Good morning, everybody. Right now, I would like to start a recap for the week 3 session 1. I feel very sorry that the first time I did it, I do not actually handle it properly because I forget to set on the slideshow. So some about 30 minutes of it actually are not pretty good. So right here, I would like to retap it. And first, I would like to show you the course that taught by Professor Michael Scott, and he's with University of Rochester. I believe this university is in New York State, and they have this course 454 Programming Language Design and Implementation. And I believe this is the equivalent course for our 46K. And as you can see, they have some assignment. If you are interested, you can look at it. But okay, and then let's look at their class note. They have class note on each of the chapters. So they pretty much cover from chapter 1, 2, 3, 4. Take about half of their time, and chapter 5, 6, 7, 8, 9, 10, 11, 13. They are using about the same structure with our course, except that they have the 11, 14, 16 added to their schedule. And if you look at their schedule, actually they have the introduction, syntax, semantics, and then they jump to functional programming language. I believe it's in OCaml, and then come back to names. So basically this name binding and scope issue actually can be moved with the data type or composite data type. But somehow this book play too heavy on this chapter 3, and actually that's why we spend too much time on the first time. So today I'll try to limit myself and try to focus on the topic that is related to our course and actually related to the compiler design. That is with our main stream for our course. Let's get started. Chapter 3, name, scope, and bindings. Overview of name, scope, and binding. That's lecture C0. Name is used for variable, constant, and sometimes it's like operators, or sometimes keywords. So it's for ID. And binding is the data memory association for the variable or ID, and actually this is the relationship between the name and the memory, and scope is the lifetime between the two. Is the lifetime for the binding. So a name is exactly what you think it is. Most names are identifiers, and sometimes it's keywords, sometimes it's symbols. Like plus sign can also be a name. The reason why plus sign, minus sign can be a name is because this sign actually work like a function. So you can say plus sign is equivalent to plus plus function with a and b two parameter. So that becomes a plus b. So plus sign in some language like C, C double plus, I believe, will be can be overloaded, and you can redefine the functionality of this plus sign. And binding is an association between two things. One is the name, and the other is the thing it names. So we can call this as object or entity. So between the name and the object can be a variable, can be a constant, can be a function, or sometimes we call it closure for the reference of function. And the scope of the binding is the part of the program textually in which the binding is active. So the scope is a part of the function, part of the program in which binding is active. So it's the valid the region of the program that that binding is served, and out of region actually the binding is inactive. That's how we call it as scope. Okay, so here's a name called John Smith, and this John Smith may be bind to this military person, and maybe this is the year 1914, 15 for First World War. But the same name can be bind to a kids that play cosplay for Superman or something, or Iron Man, I don't know. And then the same name can be bind to a office person or a basketball playing kids. It all depends on when you are talking about this name and who you are actually naming him. So that's how this binding works. And binding has locality. Some part of it, this binding is valid. Some part of it, this binding is not valid. So that's what the name, binding, and scope work. So in this chapter, we mainly handling about when the variable is defined and when the variable stay valid and when how this variable is associated with memory. And these issues, I believe why this professor put it in chapter 3 is because when we do compilation, we need to know each of the individual variable is valid at certain region. We need to know when the variable is valid and when it is not. So when we do compilation, we will know whether we need to report the error message or not. So that's the purpose for us to study binding right here. So let's look at the name, scope, and binding for the first overall view. We have the static instant member. That's the first level of the scope. Static member live in the non-heap area, or we call it permanent area. Depending on the language, some of the language is permanent. If you actually load the program image, then actually you start to share the data or the function. At that time, it's already valid. We call it static. And for instant member or instant variable, that is stored in the class memory. And class memory actually is what? Actually is in heap. And we allocate some memory for the object. Those part we call it class data. And actually the object will be existing only when it is instantiated. So the scope is different. Static always in the memory once the class or the program is loaded into the system. And instant variable or object variables, they actually will not exist if nobody created. So it's instantaneous, or it's actually not always there. It's related to the instance. That's the first thing we talk about the scope. Depending on how you create it and how you classify it, it's a static or instance member. Second, you would have the global and local. Global, you have namespace, you have package, you have module. These are different ways for you to package your program. So you will have different level of the compartment that will actually separate your program parts from each other, and that actually will create some local variable, some global variable, some shared variable, some private variable, and they are within a module. You may have global variable, local variable that's global to the module, or local to the module that depends on they are parameter, they are functional level, and at the functional level they are parameter list, they are functional level but local variable, and they are loop level variable, they are block level variable. So there are 4 or 5 different level of the parameters or variables will be defined locally, and then at the module level, package level, or namespace level, you all have the global level variable, and at even higher level, you can share whatever variable that can be shared to other package or other module, and that's sometimes related to import and export. So we have two things. One is by the instantiation or creation of the variable, you can divide it into static or instance. From the program location, you would have global and local, and then you will have the share and private data if you look at the package level. And other than this scope issue, we also have the visibility, public, protected, default, or private. And actually these will not change the scope. Okay, if you define your variable, the scope will not be changed. But these will prevent people from looking at your program or using your program. That's the visibility. So the visibility level, you have public, protected, default, or private. Yeah, you have several different levels. And public actually is open to everybody. Protected, you actually open to only the class or module that inherit your package. And your program, your class, I'm sorry. And default actually is open to the same package. And private is private to your own class or module. And this definition is based on Java. And I know C#, C++ all have different visibility definition. But let's pick this for now. And public, sometimes in UML, you have a plus sign. And protected, you may have punch sign. Default, you have tilde, but sometimes it is omitted. And then private, you have minus sign. Excuse me for some water. Okay, let's continue. The next thing I would like to show you is a diagram, and it will show you how things are located. First, we have main program, and in the main program, we have actually a variable called number of students, and it will store some value in the main program's location. And if this is a static variable, program, you would actually store some of the data or constant in the constant pool, but you will put the local variable into the stack, code stack. And then in the code stack, you may have this, and if you use the constructor of the student class, you will create a reference. So the reference will also be pushed into the code stack. And this is the code stack. This is the code stack. And after the creation of the instance of the student class, you actually create a student object. And that student object has age and name. And actually it is located in a heap. That's one object over there. And then, because you call the student constructor, actually in the student constructor, you will come with the default reference that's implicit. Actually, you have this reference, but it doesn't show up in your program. That's actually what I call implicit. And this implicit reference name is called this, and you can point into the object that it created. So this is a hidden or implicit variable. And then you actually pass the name in and actually create an age for this object. And the name actually is also a reference type, is like pointer type, and it is pointing to the heap. And the heap actually has the string in there. But here actually is, I should say, it's not 100% correct. If this string is a interned string, like you have double quote sign, and this will be stored in the constant pool instead of a heap. And it will be heap only if it is created by the string object. So you have new string parentheses Jiang. In that case, that will be put into the heap. If you have name, a string name equals quote, double quote, Jiang and double quote, that will be stored in the constant pool in your method area. And this student constructor may call setName, and setName because it's a instant method in the student class, so it will also get access to this reference, and this reference will point into the student object. Again, this student reference is hidden, and you can also have the reference for a name that through the heap as well. And again, this can be here or can be in the custom pool. So that's how these different variables store, and it also show you at what time, at what level, say in the setName level, the binding this is related to this call. The binding for name is for this variable to Jiang. Now this one is inactive. Actually, they probably means talking about the same thing, but this is a reference variable in Power if you call setName at the time you call the setName. And student constructor actually calling the setName, the reference will be inactive until this setName got popped out, and then this student will return to active. Let's move on. Binding time is the point at which a binding is created, or more generally, at the point at which any implementation decision is made. Language design time, or you can have language implementation time. Some of the binding is created at the language design time, and that actually is something like that interned or literal data. Those are stored in the constant pool, so the binding has decided at that time. The scope also be decided at that time. Language implementation, sometimes like we have the mesh.py in Java, or some constant defined in certain module, or as system.in, those type of input string. Those are decided by the SDK, software development kit, and actually it is in the language implementation time. You will decide this, and something like arithmetic overflow that will be handled by exception, and that relationship is decided by at the language implementation time, something like that. So here I would like to talk about static and dynamic binding. And for static binding, we actually call it early binding, and the binding is decided at the compile time. And dynamic binding, we call it late binding. It is decided at the runtime. And here we have two examples. And if you have one object, geometric object that is pointing to a circle data type, and this circle data type actually is a object, and if you actually in the object you call area, that area actually is its own copy, so that is actually a local copy. Actually, that's an instant copy. So that is static binding, and that is decided at compile time. But if you have the polymorphic method, actually you use the geometric object x pointing to the same circle, but you did not cast it, and that object is treated as geometric object. And at that time, this x.area function, when at the runtime, it will go to the dynamic chain for the binding, and then it will find the copy to run, and it will be in the circles copy, but that is decided at the runtime. So we call it as dynamic binding, even though they may get the same copy, but that is actually decided at the runtime. We call it dynamic binding, and that's because this method is actually a polymorphic method that allow the object using the parents' reference or grandparents' reference to be able to run this object and then get the current version of the implementation for that function. And in addition to static and dynamic binding, we have parametric binding. That means that when we call a subroutine, you have actual parameter and formal parameter. Formal parameter means you have, say, maximum of A, B, C, 3 variable, and we have integer A, integer B, integer C. That parameter is called formal parameter. And when we call it, we have maximum 1, 2, 3 number. Those 3 numbers are called actual parameter, and that's called parametric binding. And okay, that's parametric binding. Another kind of binding is polymorphic method binding, and it's also called as dynamic binding. Let me explain this in details. So right here we create a color point P. That's a new color point, and it comes with the data, a class, two xy, I believe is coordinate, and then the color, that's color red. Color itself is a object, and then this color point actually is a this P is a object, but that object actually pointing to a class. That class actually is the colored point class. And in the color points class, there is no definition for get x and get y, but it has a superclass called point class. And in point class, we have get x and get y. And when this P object try to run get x, it actually will search for the color point class for the get x and get y, but it cannot find it, so it will go up to its parent pointer class to get the copy and it run. And by doing this, you have the inherited chain from object to point class to color point, and color point is the leaf class, the lowest class. So when we search for the polymorphic method binding for dynamic binding, we start it from your local copy. And if it doesn't have the implementation, we go up to its parent to get the implementation for the method. And if it still doesn't exist, you go to its grandparent, something like that. We call this is a dynamic chain for the dynamic binding. Next one is parametric type binding. In some language like C, Sharp, and Java, we allow the generic definition. So certain class, especially for those container type, usually allow the parametric type binding. And right here, we have one type variable. You can assign type argument over there, and you can also call it as type parameter. So that parameter will pass into your class, and your whole class will be operating on this type. And because this is a type variable, so it actually should be a reference data, and string is also a type variable. It's also a data type, and that is of object type. So since this is an object type, and that actually is for reference, and the size of the reference address is of the same. So this is actually at the compile time, it will reserve the same amount of space for this reference. That's only a pointer, and then at the runtime, it will locate the type that you pass in for you. And because at compile time, you pretty much don't know who is calling this. Actually, is calling this is passing the type to the your class, but actually it's okay. And also, the class may not be available. It could be from different package or something. Could be an external import or something. But here we have one slice for the C++ namespace for binding. You may have a statistic function, for example, the standard deviation, and you may be in the namespace for stats. And stats may have one package that imports stats that has another environment, and that environment could be for that package that may have the base namespace on top of it. Then there may be a global environment variable. Then there may be a package stats for it. Then they may have several different package being on top of this. And then they have a base environment. Then they have finally empty environment on top. So this actually form a chain of the environment setting for namespaces. Excuse me. And when you try to find the copy for binding, actually it started from the closest one that you directly been included. Then if it's not there, you try up one level and down to this whole chain. That is how this namespace for binding is working. And C++ has virtual function for dynamic binding, and it's similar to Java. And you have the base class pointer, 2 pointers, and this 2 pointer may point into different object of different class, derived 1 and derived 2, but their base class are the same. So when you actually need to run certain function or method under these two objects, these two objects may be used under same base pointers, and then when they are run, they need to find their own copy for their implementation of the method. They may be that two methods may be the same name. Then you will need this virtual pointer and v pointer and virtual table to find the copy for its function. So v pointer is the v pointer which point to the virtual function for that object. So it's pointing to the virtual function. And this virtual function table actually contains the address for the virtual function for each class. Then at the runtime, you will find the physical call stored somewhere. And this is how they resolve the dynamic binding for C++ polymorphic methods. Now, let's get started for C1 binding. Binding, as we said, it's the association of your name or ID with the memory. So there are several different binding time. You can have static binding time, that is language design time. In most language, the control flow construct the set of fundamental primitive type like int that actually you will bind at the language design time. The available constructor for creating complex type, and many other aspects of the language semantics are chosen when the language is designed. Language implementation time. Most language manuals leave a variety of issues to the discretion of the language implementer. Typical example including the precision of bits. Okay, that actually is implementation time. For example, C language, they may have different standard IEEE 754 for the floating-point standard, but other implementer may not follow the same standard. In Microsoft Windows, you will use one standard. Poland may use another that I'm not really sure of. But at least that will be an issue that actually the binding is at the implementation time. And the I/O usually is another issue for the notion of file on Windows and on Mac and on Linux. They are all different. The organization and the maximum size of stack and heap, that actually also related to the process image that is allowed by the OS. The handling of the runtime exception and arithmetic overflow, that is also related to the OS interrupt operations. Program writing time, that's depend on the programmer. Compile time, compiler choose the mapping of high-level construct to the machine code, including the layout of statically defined data in the memory. So compilation time, you will actually need to depend on the compiler. It will actually choose different machine code to actually locate the memory and associate with your ideal variable. The notion of binding time, link time, that's long time. Actually, this is dynamic binding. There are two major ways of compilation. One is link, load, and go. That's compile, link, go type of program. That's static linking. The other kind is load and go, and actually is just going pass to the just-in-time compiler, and then link and go. That's dynamic binding. So you have link time. Most compilers support separate compilation. That actually is for separate compilation. That actually is a static compilation, and depend on the availability of the library and standard library. A library of standard subroutines. A program is usually not complete until various modules are joined together by linker, and the linker could do it at a static time. And also, if you are using the just-in-time compilation, the linker will actually get its code until you load it and run. So actually, they are load time. And actually, to this point, the operation system load the program into the memory so it can run. And most modern operation system distinguish between virtual and physical edges. Virtual edges are chosen at link time. Physical edges can actually change at the runtime. So at the loading time, they will still have the virtual edges versus physical edges issue, and that actually will bind your variable to different location. Runtime is actually a very broad term that covers the entire span from the beginning to the end of the execution. So binding of value to variables occur at runtime. So do host of other decisions that vary from language to language. So here are different dynamic binding time. So let me show you 4 different ways of compilation and the run procedure. First, let's look at the traditional C, C++, and Ada. It's compile, link, go process. So you have multiple source code. You can compile individually, and then it become object code. Or you can actually directly compile it to the machine code. But let's assume that now it's some sort of intermediate code or object code. and you can actually link the library functions, a string copy, file open, that kind of different function together by the linker and load into the memory and run. So this is called a compiling go process, and this type of the program usually is for static binding. And when the Windows when the Windows system become popular, and we started to have dynamic linking library, then the load unit and the Go unit actually start to link some program, and that's actually under the Microsoft Foundation class, and it's actually breaking the compiling Go structure. But anyway, that's another trend for CC++, and that actually at the runtime allow the dynamic linking feature. So CC++ in the past 20 years start to pick up the dynamic linking as well. But actually that is one pass. Actually that's one pass other different from this Java and C#. And let's look at the C# now. The C# environment and Visual C++ and also .NET and Visual Basic, they are in one .NET framework, and somehow they allow the Visual to have dual pass compilation. So this pass of compilation still being allowed in the .NET framework. So let's look at this C++. You can compile, and then you link, and then you execute. And at compile time, you may link the DLL, the dynamic linking library. And actually, when you link, and you may actually try to fetch it, but at the wrong time, when you run the Windows program and you click something at the wrong time, they also may be linking some library for you. That's the Microsoft Foundation class for the Visual C++. And later this approach being integrated with C# and .NET. Then you have a C# file or your C++ file in the .NET framework, and you pass through the compiler. Compiler generates some sort of managed assembly. That's intermediate code, is .dll or .exe. Then it's loaded by CLR, and then CLR use .NET Framework class library. So this actually is the runtime dynamic linking, and then pass through the OS to run the machine code, and that converted to native machine code to the OS. So actually, .NET Framework allow the dual pass for C++ and C# Visual Basic, and C# Visual Basic is on this new .NET Framework pass, and C++ is on both paths. And Java has Java Virtual Machine, so it's actually a compile, load, interpreted, that actually by Java Virtual Machine, and then linking, and then just-in-time compile go. So that's the process of the Java system. You have Java program, you go into compiler, you have the intermediate code, bytecode, and then that actually stores somewhere. And at the runtime, you load your class. After that, you interpret your bytecode and perform just-in-time compilation and link with your library from JRE, Java Real-Time Environment, and that's similar to this .NET Framework class library. So you have a runtime dynamic linking and actually go to hardware to execute it. So these two approaches are similar, except that this always requires the Java Virtual Machine. And at last, let's talk about this JavaScript compiling Go process. JavaScript is executed by JavaScript engine on browser. So actually, it is a interpreter-based system, or you can only execute sequentially, because we don't know whether the OS is supporting multi-threading or not. So assuming that this JavaScript can run on every device from small to very big system. So the object actually is from the DOM, the document object model from your browser, and that is the object. And your JavaScript actually will get the object from there. So there's a object and the JavaScript relationship. We'll show this actually later as well. But now you have your JavaScript code, and then you link, and actually that is a linking for finding the library with in your JavaScript engine, and then you try to run it. So it actually is similar to compile link go process, but that's because it's run sequentially. It do have the event loop, but that event loop is sequential loop to try to mimic the multi-threading environment. But I'm not sure currently there is any version of a parallel JavaScript at all. Implementation decision. At runtime, we need to bind the value and the variable, and actually also need to decide the size of the string array to allocate the memory size, and also need to decide the static, heap, and stack size. So these implementation decisions are related to our compiler or language design. Basically, you need to decide how to bind it, and also the size of the data, and also where it should go. These are the three major issues for the name, scope, and binding section. Actually, it's data type. It's a data related issue in compiler. And we will do the following at different time. We have to decide the implementation issues. You have the program startup time, that's a load time. Module entry time is used, and usually the program started up time is loading of your class. And module entry time is when you actually run your function or run your module that has some content, actually try to import something for your module. Elaboration time that you actually is when you declare some variable or some function, and procedure entry time is the functional code for the code stacks, and block entry time that's related to your block level, run over, whether to continue or break, those type of things, and each statement you have statement execution time. So there are different level of the program the implementation issue for this memory and variable. Then scope and binding. The terms static and dynamic are generally used to refer to either its runtime or compile time. So static means compile time. Dynamic usually means runtime. But both of them are actually very coarse terms, so it's hard to say whether which one is which one, because the compilation process, compile link go, may actually go through multiple paths or different paths. So you really don't know what. There's no clean-cut differentiation between the two, and that's because the compiler become more and more complicated. In general, early binding time is associated with greater efficiency. This is talking about the compile the static binding. Later binding time associated with greater flexibility, because you can always find different library for you, but that will consume more time. Compiled language tend to have early binding time. Interpreted language tend to have late binding time, and hybrid type that actually take advantage of both. So that's why currently most of the language are going for hybrid. You have compilation to the bytecode, intermediate code, PYC code, and then you have interpreter to finish it up. And the interpreter may have its own just-in-time compilation as well. So that makes things more complicated. Scope rule. Scope rule is to control the binding. It's fundamental to programming language. Actually, is the ability to name data, to refer to data using symbolic identifier rather than the address. So scope rule decide which copy of the memory should you associate with your name, that is your variable or ID. Not all data is named, so there are maybe some temporary data, or there might be some something like anonymous function or anonymous data that actually being used in the middle of your program, and they don't have a name. For example, the dynamic storage in C and Pascal is referred by pointers, not a name. And that actually you have pointer that has body, but the body doesn't have a name. Here, I talk about 4 types of different polymorphism. Polymorphism is the way that to support your function to have multiple implementation. Excuse me for water. And there are 2 types of polymorphism. One is ad hoc polymorphism. Ad hoc polymorphism assigned by programmer. Universal polymorphism, that's assigned by language definition. So let's look at the ad hoc polymorphism first. First, let's look at this coercion polymorphism. Coercion polymorphism is data casting. So you cast your floating point number to integer. That is narrowing of your data type. And you cast your integer to your floating point. That's widening of your data. We call this coercion polymorphism. Actually, it's just casting. So this is easy to understand. You actually, by casting, you will be pointing to different memory size. So that's the coercion polymorphism. Second, we have overloading, overriding polymorphism. That's redefinition of function or making multiple copy of the function of different, accepting different parameter. So that provide variety using this overloading, or you redefine, that's overriding. So you have you can work on the operator or functions for this. That's the overloading, overriding polymorphism. Third type is inclusion polymorphism or subtype polymorphism. That is actually the inheritance polymorphism. And inheritance polymorphism has 2 types. You have the interface type, or you have the class type. And inclusion polymorphism actually will make the dynamic binding occur when you pointer your reference data type pointing to different type of object of the same reference type. And then parametric polymorphism, we are talking about generic or generic data type. This is talking about the type variable, so that some container class like array, or I'm sorry, like list or vector or queue, they can share different data type using the same class definition. So that's type variable. We talk about a type variable already. That's called parametric polymorphism, a polymorphism created by type parameters. Now let me check whether my recording is still going on. Take a short break right here. Recording is on. Okay, let me go back. Now we are on the lecture C2, lifetime and storage management. Lifetime and the storage management. Key event in memory management, we have creation and destruction of object. We have creation and destruction of binding. Actually, this is one is the data, one is the association of the data in the memory with the variable, and then the next one is the activation and reactivation of binding. that may temporarily be unavailable. Third one, reference to variable, subroutine, type, and so on, all which are using binding. So creation and destruction of object is like you use the new function. And then creation and destruction of binding is you have assigned a new constructor return value to a certain reference type. And then activation and deactivation of binding is when you have context switch of different procedure, then actually some variable will become temporarily unavailable if you jump into different binding environment. And then you have reference to variable, subroutine, and those are easy. Lifetime and storage management. The period of time from creation to destruction is called the lifetime of a binding. If object outlive binding, it's garbage. So if your object is still there, but your reference has been abandoned, then that object become garbage. So an object that has nobody reference to, that is a object is a garbage. A binding, if the binding outlive object, then it's dangling reference. You save the reference variable, but actually your object had already been removed. That's a dangling reference. A textual region of a program in which binding is active is scope. So the program that you can use certain variable that is called is scope. In addition to talking about the scope of binding, we sometimes use the word scope as announced by itself without indirect object. So scope itself can be announced, can be counted in our computer world. So now let me show you different kind of binding. First, right here is a Java code. We have the charge class, that's electrical charge. So you have the location variable rx, ry, and you have q, that's a charge. That actually is an instant variable, and the instant variable being stored in the heap area inside the object data. So it's in heap area. Once this object is created, an object of this charge type is created, there will be a copy for a certain charge that actually has this data type. It's inside the object data. And then second one, you have a parameter for a instance method, and that actually when this method being called, there is a return address being stored in your call frame, and then this parameter also exists in the call frame, but reference parameter is on top of is at the bottom of the call frame, and there might be instance variable that will be on top of the return address, and the blue one will store the return address. So these two, the order are different. And anyway, these three will be anything related to the method when it is called is stored in the call stack, and the method body is stored in the method area, its own call body. So it's already ready in your virtual machine somehow. And then we have the static method. Static method is stored in your method area SL. But when you create an object, the reference type is stored in the runtime stack, while the object itself stored in the heap area. And then there are some static variable that's not shown, that would be storing in the class data, in method area. So lifetime and the storage management. We have storage allocation mechanism. We have static, that's in the method area. We have stack, that's in per thread memory. We'll show it in the next page. And then we have heap. Heap actually is in this heap space. And static allocation for core, you have core being stored in here, global variables is stored in here, constants stored in here, and then static or on variables stored in the class data over here, something like that. And heap, the stack, the central stack actually is stored in your thread stack. It is stored in your thread per thread image. And Java Virtual Machine has the stack area, and each stack is staying in one thread. And there is a heap, and the heap actually store all the objects. And the stack primarily store the temporary, local variable, and parameter, and the return address. So that with stack, it allows space for recursive routine and reuse spaces. And continue the previous page. Container stack frame, you have argument and return, local variable, temporary, and bookkeeping. Sometimes you have the register and line number for static links. So these are actually invisible to the programmers, but this is in more detail. Local variable and argument are assigned fixed offset from the step pointer and frame pointer at the compiler. We will show some graph for this. So right here, that's from textbook video 3.1, stack-based location of space for subroutines. We have a main program that's calling A, and A procedure calling B, B procedure called B itself, or LC, and that's conditional. But if we call B once and then call C somehow, and C call D, we will have such a stack. And this stack will be stored. This stack will be stored in one thread stack if there is only one thread executing. And you actually, every time you push in one core frame into your core stack, and you have the frame pointer, this show at the bottom for this frame pointer, but somehow this usually is not like that. Usually the local variable is under it, and the parameter, I'm sorry, the parameter for the subroutine written down over here is under the return address, while local variable is on top of it. Because local variable can grow, but the arguments and temporary from the parent procedure won't grow, so it's under it, and actually usually is shared by its parents as well. And bookkeeping won't change as well. That's under the return address. Only the local variable is on top of return address. So this call frame structure is not, it just provides the content, but the order of the address is not accurate actually. But your frame pointer is used to calculate with offset. That offset is some local variable. It provides some offset variable. Say it's like 5 bytes away from return address, the frame pointer. Then you will be able to access certain variable. So that actually is a relative addressing, and it is actually a dynamic binding at the runtime. You will load some address using the relative addressing scheme to access your variable in your call frame. And there is also a stack pointer. If you have new thing to push in, you will push here. And once you pop out D, the stack pointer will drop to here. Frame pointer will drop to here. So here this is called a call frame, and call frame can also be called as activation record. And the procedure to call it is called prologue procedure. And the procedure to finish it up, pop it up, is called epilogue. We will talk about this as well. And displacement addressing is the way to identify to find your local variable or parameters. That's displacement addressing. And the procedure to call and return is called, for this call frame, is called calling sequence. Stack and call frame. Maintenance of a stack is the responsibility of calling sequence and subroutine prologue and epilogue. And space is saved by putting as much in prologue and epilogue as possible. So if you want to save space, you need to put as much thing in your prologue and epilogue as possible. Time may be saved if you put more in the body of the subroutine. So actually, there are some trade-off that is a implementation issue for compiler. So heap, now we are on the object space for heap. Heap is for dynamic allocation. So in C language, you have memory allocation function, free function, and that's actually operating on a heap. And in Java, C#, you have constructor, destructor. Actually, that is also associated with dynamic allocation on heap. And after a while, your heap will have some free space that is actually in white. Let me see. Yeah, and then your gray one is actually in used. So you will have some several fragmentation. You have a several call fragment, and then you have a serious fragmentation issue. So you need to actually clean it up by garbage collection if some objects are abandoned already, and there are first fit algorithm to find out if you create a new object, you can find a certain slot for it, is the first fit, or you can actually find best fit to look over the whole heap to find the one best suit its size. And you can also do optimization on the heap for. So there are quite many garbage collection algorithms handling this and optimization of the heap. So now we are looking at the garbage collection. You have your root, you have global, you have local, you have CPU register. This actually, those programs actually creating a lot of different objects in the heap. And this heap over the time will have some unused object or some empty slot in the memory. So we have an algorithm called mark and sweep algorithm that will be explained in chapter 8. But anyway, you identify those parts that is not used and then clean it up using the mark and sweep algorithm. Now we are going to the memory model, lecture C3. Every language has its own memory model. Let's get started with the C++. You will have one process image or program image when you first load your module for C or C++. And then you will have instruction, that's your call, your constants or your literals, and you will have stack data that actually used to store a static data that would be used for your global variable defined in C++. And then you will have the instance call frame stored in stack. And also you will have the object data stored in the heaps. And stack and heap will grow, but sometimes you will be out of memory. And this sometimes happens when you run your program and you saw some out of memory for call stack or something. It's not kind of a warning or message. And usually that will happen when your recursive call is not handled right. And that actually will happen. Or you have infinite loop to allocate or create so many objects or so many records in your program, so your heap will be out of space, and that actually will, because you have limited size for the process image. So some OS will help to swap in, swap out, or have larger memory management when you need your program to have larger memory space. There are certain ways to get away from the limit for basic process image size, but that is for memory management for the program. And right here, I show you the basic C++ memory model. There is no virtual machine, no very serious runtime environment over here. It actually the only runtime environment that it deal with is the OS. And now we have more mature model using by .NET. As I mentioned, your C++ can put your code in the managed code in CLR, the loading service in the .NET framework, or you can run in the unmanaged code like previous one, C++, Visual C++ can run like this, the traditional way. And .NET provide a dual path for it. And your other language like Visual Basic, your C# will have different compiler and assembly, and then you compile and finish the assembly, and you have the just-in-time compiler and compile them into the running space. And actually, those are managed code. And when it is run, you will go to your operating system, and some of the dynamic linking happen when you run anyway. And your memory, you have the assembly and library assembly, system assembly, something like that is in your memory, in your system already. And you have system code space. These are the DLL help to process your code. And they might be per process address space. So this one is similar to the Java one, similar to this per thread memory. The two are similar. You have just-in-time compile code, garbage collection heap, in-memory representation type, something like that. But they are multiple copy because every process has one copy. So that's per thread. And then we have Java memory model. So Java memory model is a little bit smaller than the .NET framework, but it has the method area. You put in separate class definition, constant being stored here, static data being stored, have a copy over here, and then your method code being stored here. Every class has its definition over here when it loads to the memory. And then at the runtime, you will be forked with different threads, and those threads will have its own step. You have different code frames, something like that. And those threads may create some object. Those objects will be stored in a heap, or you will have array being stored in a heap. And string will also be stored in a heap. That's the Java memory model. This is the Java memory model. So this one actually supporting the Java compilation process. And .NET has its own compilation process, and C++ has its own compilation process. And the next one is JavaScript memory model. Java script memory model, you have a DOM space, document object model. And actually, there is another object model in browser that is the window object model that is supported by Microsoft Windows or Mac OS or something like that. Actually, those are things that JavaScript program may be able to access. Controlling of the mouse, controlling of the keyboard, something like that. That's WOM. So that's related to Windows. And DOM also have documents, forms, and different objects that you can access by the JavaScript. But JavaScript, when you load your program, that will be just like one thread. So comparatively, not exactly the same, but JavaScript memory is just one thread because it doesn't assume to be in the multi-threading environment like Java or C#, but it has its own stack. So it will store the local variable and those things like that over here, and then has call frame type of thing. And it also has an object. But in good old days, the first JavaScript do not assume object-oriented programming when the language just come out. So later, the object concept is actually some record, some sort of record, data record. So that actually has object space and where all JavaScript objects are located. And later we have the JSON, different format of the object notation, and that will also be translated to JavaScript type object in the memory. And but just assume that there is a JavaScript engine running the JavaScript, and it will refer to the browser engine for the DOM, and that's the memory model for JavaScript. Python is a pure object-oriented programming language. So all the integers and strings are object in Python. But Python has interpreter. So the objects in Python language will all be stored in heaps. Since all the data type are object-oriented, so it will be using the heap to store everything anyway in the Python. So Python just need to deal with heaps. And then the heap will actually go to raw memory allocator. And that actually, because it has the interpreter, so the interpreter actually will at the runtime will allocate the memory, but those allocator may be running some call from C language and your memory management issue. So right here is the cut. Under here is the job for interpreter that may be written by C language. But on top of it, what you see is you are talking with the interpreter. So that is actually object-based. So Python is actually divided into two parts. One part to the people, you are dealing with the object memory. On the other hand, you have the interpreter itself that is actually running like a C program. So that's the Python memory model. Now let's look at first scope rule number 1, our lecture number 4. The scope rule, the textual region of the program in which binding is active, is called its scope. In most language with subroutine, we open new scope on subroutine entry. So basically, when you start a subroutine, you actually create a new scope. And after you create a new scope, you create binding for new local variables, deactivating the global or the previous call frame. So local comes first in binding, and then we declare, make reference to variables. So you allow the local, the subroutine to create its own local references. And sometimes in the call frame, you will have these super, those keywords allow it, actually they are inherited, and actually it's in implicit variable, reference variable also existing in the call frame. Or you can backtrack to its parent to find those variables for access. So still have something you can backtrack. Static versus dynamic scoping. Remember, this scoping is different from binding. Scoping is the determination of the binding, but it's not binding itself. So right here we have static scoping and dynamic scoping. So static scoping means you determine the binding at the compile time, and dynamic scoping is you determine the binding at the runtime. So static scoping is local understanding of function behavior, know at the compile time what each lane refer to. A bit trickier in implementation, so you need to look over your code to decide your bindings. Dynamic scoping is hard to understand how this happened and require finding name binding at runtime, but it's easier to implement since you just look at your global variable who is now actually running those kind of things. You will be able to determine your binding. So static scoping, because active bindings are statically linked to block lexical ancestors binding, this scoping method is probably the most intuitive binding mechanism and is featured in most common language, modern and common language, class object-oriented language, just like Java, C, C++, and C#. So static scoping, actually, you just need to know who is calling me right now, and I will base on that calling structure to determine where the binding should be. So let's roll back a little bit. You have this namespace chart, right? So basically, you know who called me and who is behind me. So this kind of the scoping rule, you have this namespace chain ready for you. You can decide, okay, right now who is active, who is active. So I am using the scoping rule by this chain. So that's easy to understand, very intuitive. But in implementation, you need to do such a long chain for static scoping. But dynamic scoping, on the other hand, don't have this kind of long chain. It has a environment variables to decide. So that's a different story. Let's go back. So dynamic scoping binding are dependent on the order of the subroutine call. So actually you need to check the call frame, those kind of things. But since it's decided at a runtime and you just need to keep track of the global variable and the stack and need to look at the global variable and stack, you will know where the data is. It doesn't care about your environment namespace chain in the compiler. It doesn't care about that. Scope rule on subroutine exit, destroy the binding. You actually pop things up and reactivate the binding with the global variable that is the word activated. Ogo 68, elaboration process is the definition of the elaboration means the declaration of the variable. So it's a process of creating binding when entering the scope. And ADA, repopularizing in terms of elaboration, is storage may be allocated, task started, even exception propagated as a result of the elaboration declaration. And anyway, these two are not that important. They are out of date already. Scoping rule, reference environment. Okay, we introduced one more term, reference environment. This term is very important. Reference environment is the set of binding. It's called the current referencing environment. So to be short, this is the reference environment that you have right now. So once you pop up out of one namespace or something like that, you actually change your reference environment. So reference environment also depends on what are called binding rules. I'm sorry, I started from here. Reference environment is the set primarily determined by static or dynamic scoping rule. A reference environment generally corresponding to a sequence of scope. That is the chain we show. That can be examined to find the current binding for a given time. Reference environment also depend on what we call binding rules. Specifically, when a reference to a subroutine S is stored in a variable passed as a parameter to another subroutine or returned as a functional value, one needs to determine when the reference environment for S is chosen. That is, when the binding between reference to S and the reference environment of S is made. So anyway, that's about a binding rule. And there are two options for binding. One is deep binding, the other one is shallow binding. So based on the environment you have, you still have deep binding or shallow binding. That actually means you have a choice of determine the reference that is first created or is finally used. So that actually is different text where it's used or whether it's declared. There are two different binding way. Scope rules with static scope rule. A scope is defined in terms of physical structure of the program. So scope is defined by the structure. The determination of scope can be made by the compiler, or binding for identifier can be resolved by examining the program. Typically, we choose the most recent active binding made at the compile time, and most compiler-based language use the scope, static scope rules. And actually, dynamic scope rules are very few, are very not really often used. Scope rule, dynamic scope rule are usually encountered in interpreted language, but actually not many of them implementing them now. Even Lisp only has early dialect that assume dynamic scope rule. Such language does not normally have the type checking. This is one problem at the compile time, because the type determination isn't always possible when dynamic scope rules are in effect. Static variable in C. So in C language, we are able to declare a variable that is static, and that will be stored in some static area instead of becoming a local variable. So when we call this method, we will be accessing this n that is in static data area. So every time we print the current value +1, and then actually we advance it. So initial value for this n is 0. On the first time we print it, we got the 1, so we print now L1. And then the second time we call this, we actually will print out L2. So this function is used to create a label. Those labels are L1, L2, something like that. And this is how we use the static variable in C. But if it is not called, we will not advance n, and only when the n is called, this variable always get the previous calls value +1 and then print it out. Now let's look at scope rule number 2. Nested subroutines. And nested subroutine is very important because that determines the scope of the variables. The classical example of static scope rule is mostly closely nested rule in block structure in languages such as Ogre or Pascal. An identifier is known in the scope in which it is declared, and in each enclosed scope, unless it is re-declared in this enclosed scope. Let's look at the script on the right. We have A declared as 1, so A equals 1 is in power for the whole purple area. So when we print out A, that's 1, and we declare B as local variable, so B is local to this code block up to here for B equals 2. So when we print out B over here is 2, and then C is declared to be green area. So when we print out C outside this green area, we got nil. Nil is the null for Pascal language. And then we declare D equals 4. But since this D is not declared as local to green, so it actually has a scope of this purple area. And when we print out D, that is 4. But this B actually is local to red. So when we print out B over here, it becomes nil. So it's not available over here. Nested scope loop. Right here, as you can see, we have a big procedure, the procedure P1. And the scope for P1 is actually from here to here. And then for the parameter A1, that's argument list 1, will be coming from the beginning of P1 to the end of P1. And then we have procedure P2. That the procedure P2's lifetime will be the starting of the procedure P1 to the end of the procedure P1, because procedure P2 is defined within P1 according to the rule for Pascal. And actually it's something like this. And then for X is a variable for P1, and that is defined inside here. So actually it's right here until the P4 declare a different variable called X, same name, then it's interrupted. And at the end of procedure P4, actually the F1, this function is inside procedure P4. After the end of the F1, actually we resume this global variable X, so it's just drop this period of time. And then for P2, it's defined within P1, so the lifetime is as long as the P1's scope. And then A2 is defined as the argument list for procedure P2, that's up to here. So A2 scope is the beginning of the procedure P2 to the end of the procedure P2. And procedure P3 from here to here. So the procedure P3 scope is beginning of the P2 to the end of P2. And A3, the argument 3, will be beginning of P3 to the end of P3. So that's the scope for this. And you can look at the other procedure and the variables. But what happened is, this is for the scope for Pascal or Ada type language. In Ada, for example, a name may be prefixed by the name of the scope in which it can be declared. So basically, if you want to access the local variable or global variable, you still have a way to do it. For in Ada, you can use the my procedure.x. It looks like a recurse data video, but actually in this way, you can access the local variable. For example, right here, if you want to access F1's x, you can use my procedure P4.x or F1.x. Now you can access that. But of course, this may not be the Ada case. But for Ada, you can do that. In C++, you can access the global variable by using double column and X. For example, you want to access this one, if this is C++, and there is a local copy right here. But if you want to access the global copy, you can use double column. That means no namespace variable X. Then you can actually get a global declaration of X, and regardless of whether there is an X in subroutine or not, you will be able to access the global X. That's for C++. Scope rule will see classes relative of module. So class is similar to module, but is better defined later when discussing abstraction and object-oriented language. These have been even more sophisticated scope rule. These have even more sophisticated static scope rule for classes, but that actually make the data safer. Euclid is an example of a language with lexically nested scope in which all scopes are closed. Rules were designed to avoid alias, which complicate optimization and correctness argument. Okay, note that bindings are created in a subroutine are destroyed at the subroutine exit. So that actually is the lifetime for the binding. When the subroutine finished, the binding will be finished. The module of modular ADA give you closed scope without a limited lifetime, and that's the purpose. That's the feature for these two languages. Binding to a variable declared in the module are inactive outside the module, not destroyed for ADA and the modular. And the same sort of effect can be achieved by many languages with on or static. So this is for C you have static, for Ogo you have on, for ADA and the modular is a built-in feature for closed scope. But for Java and some other language, actually you don't have it. If you don't have this. For the C, actually you have different prefix or different indicator for you to access those static variables. We'll talk about that later. Access to non-local variable with static link. We are going to talk about this static link. Each frame points to the frame of the routine inside which it was declared. In the absence of formal subroutines, correct means closest to the top of the stack. So the correct instance usually is on top of the stack. You can access a variable in the scope K level out by following K stack link. Then using the non-offset within the frame that's found. This is hard to understand, but actually that means that if you want to access a certain level K variable that's lower in the stack, you will be able to do that if you have the level K static link and using proper offset within the frame of the lower level K level. We will show this in the diagram. That will make things easier to understand. So right here, let's talk about the local variable. For local level, you have a frame pointer register pointed to current call frame, and that could be the base plus index. For you come out with a frame pointer, and you will have displacement, and that displacement is used for the offset from the frame pointer. So you have AP frame pointer plus displacement that's offset plus or minus, and then you sum up to access the memory. That's the way you access the call frame's data with certain the register plus offset. So you have two register, base and index. Usually the base is used for the a certain program or a certain call segment, and index is for certain relative address to the call segment. For example, you have a certain program that's starting with the base registers the location, and that could be assigned at the runtime, and the compile time you would have the relative address from the starting point for your program. So these two are used like that. But what would be about a non-local variable? That is some global copy or some local variable that's static. So we are going to talk about a static link now. So right here, let's me show you this static link. Static link, okay? We have an A procedure that called B and E. So it called B and E, but B and E also have a method to access to procedure A. Then B calls C and D. So C and D are children for D, so they also have a static link to B. So what are the static link you can use? There are 3 different kind of static link. Number 1 is the static. Now, I would like to show you the static link. So go to this page 46. Right here, this is the first way to define the static link. This N will be stored at the static area, your method area for C language. And we have 3 types of the static link. That one is the global static that will actually access the global variable static you store at the global static. And that one actually belongs only to the function, but it will be stored at the global static location. And right here, we have the static access its parent that define it, and or the caller that call it. Second, we have the super. Super is the parent that define you. So for example, we have a bar function over here, and then its upper level will have this to go to there. That is, you're the one who define you. That's super. And there is another one called caller type. You have this is current function or current module. That caller is someone who call you. And then this function, main function is x equals 3, full, call full, and full come here. And then execute this. And inside here, we have this function bar, and bar is called by this guy. So you will go to this. So that's the way D go to the B, that's called it. So you have 3 ways to access the static. One is the global static. You use the static variable. You have super, that actually is the one you define you. You have this, that caller is someone that call you. 3 different static link. Let me try to find the one. Okay, I keep up. I cannot find the version. If we see it, I will let you know. There is a version for the static definition. I keep up. So let's move on. The next one is scope rule 3. Scope rule in a block. Declaration order. Declaration order in several early languages, including Argo 60, is require all declared declaration appear at the beginning of their scope. And Pascal modified the requirement that the name must be declared before used, and it used the it used the scope by using the scope label. So for example, we define a constant n, that's the green label, and we define another n, that's blue n, that's inside this main function. It is procedure full. And this n will be valid inside this whole blue area. So if there is a constant m equals n, this n will not be the outside n, it will be inside n. That will give you n equals 20. So that's the power, that's the scope of n20. And n10 is only outside of the n20's range. So this may create static semantic error, and local constant declaration hides the outer n is overridden. So that's the something the rule for the Pascal, and it's not really popular right now for this kind of rules. So the same problem would happen if we have a constant definition for n equals 10 right here, and we redefine the n to be real over here, and then the one you actually will declare for this n equals n
same thing, you will be accessing this one. You'll create a static semantic error. So Pascal says that the second n covers a whole full region. The semantic analyzer should complain about line 5 that n is being used before its declaration, but for Pascal, it actually will not. Well, it is very confusing. It will not complain. Declaration order. For other language, most of the other language after Pascal, the kind of the scope rule is not used. So for C language or Java language or Ada, actually no such semantic error because we will have the scope after its definition. So if we have the exception handler or exception object, then the exception object's scope will be this dark green area. And then if we have declared a local variable inside the A method, but right here on this line, then this local variable will be valid only on this yellow region. And if we have a parameter defined in this A method, its scope will be this light green region. If there is something inside here, share the same name with it, then this parameter will be overwritten. And then the global instant variable, the scope will be the whole class. And then if there is certain overriding variable, then this global definition of the instance will be overridden. But somehow you can use this or super. These are two steady link for Java that you can still access the one on this instant variable definition. So, and in C#, it's actually using the same scope notion for Pascal. That's a whole block scope, and that's something like this. So remember, C# share the same feature with Pascal. And declaration order in scheme, in the interest of flexibility, modern Lisp dialect tend to provide several options for declaration order. In scheme, for example, the lat rect and lat star constructs define scope with respect to whole block and declare to the end block semantics. So actually, for scheme, it actually accepts both. Let rect and let star, actually they have the whole block and the declaration to the end block. So the whole block is Pascal type, declaration to the end of block, that is actually the C type. And these two types of scope will both be adapted by scheme. And right here we have one example. The outer scope A defined to be 1, inner scope A defined to be 2, and B defined to be A. So B and A actually share the same level, but when we access this A actually is defined by this A equals 1, and then when we return B will be the A value that is 1. Hence, the nested declaration of A and B don't take effect until after the end of the declaration list. Thus, B is defined. So A equals B is not in effect until the second one being finished. So then you finish this last statement. And so that A actually is using the higher level A. That guarantees that these two lines are actually equivalent. No one is ahead of the other. That's the feature for functional programming. The redefinition of A had not yet taken effect. B is defined to be the outer A. The code was the whole, but as a whole return 1. Declaration and definition. For recursive type and subroutine introduce a problem for language that require name to be declared before they can be used. How can the two declarations each appear before the other? So one is declared and then called by the other one, and another is declared called by another one. So each other actually will fighting for the order. So C and C++ handle this problem by distinguishing between the declaration of an object and its definition, so that coroutines can be handled. A declaration introduces a name and the index and indicate its scope, but may omit certain implementation details. A definition describes the object in sufficient detail for the compiler to determine its implementation. So two-part declaration only show the name and being allow it to be used by other people. Definition give you the body of the function. And if a declaration is not complete enough to be a definition, then it is only a declaration. Then a separate definition must appear somewhere else in the scope. So you can either define it to be so fine, so it will become a declaration plus definition. Otherwise, you can just, otherwise anything not complete enough will be considered as a declaration, and then you need to have a separate definition. So right here, we show you two examples. On the left-hand side, we have struct manager, and this manager is a record type, but the record definition is right here. So we only have a declaration. But this declaration manager is used by both this pointer boss. And boss actually is a pointer, but since pointers are of the same size, that's 4 byte integer, the compiler could determine the implementation of employee without knowing any manager details. So you don't really need to know the whole structure. You only need to know the size of the pointer, that's 4 byte, and that's good enough for employee to store, to reserve the enough space for this pointer. Excuse me. On the right-hand side, we have the so-called functional call or coroutines. We have a subroutine, this tail or function declared right here, and it's called by another function list right here. But this tail has not been defined yet, and thus this will only be a pointer to the function and also containing the reserving the memory space for the argument and the return variable. You just need to reserve that. When it call, it will call this and then access this method right here. The initial declaration of this tail, however, must include a return type and the parameter list, so the compiler can tell that the call in list is correct. Nested block. Variable declared in nested block can be very useful, as for example in the following C code. So we can actually use the braces to become a code block, and inside this code block you can redefine a certain variable temp. By doing so, actually you will guarantee this temp will not be any temp outside of this block, and keeping the declaration of temp lexically adjacent to the code that use it make the program easier to read and eliminates any possibility that this code will interfere with another variable named temp. Scope rule number 4, module class and dynamic scoping. We are going to talk about a module class, this type of thing that will actually hide the information inside it. So we will talk about the local variable and the instant variable inside certain module. and that will provide an information hiding effect. So module will help software development in parallel by a team of engineers. So you break down the one control module into several smaller ones, and some of the module may be from the library, and you will assign different engineer to work on the module. The modularization of offset of the modularization of the modulation of efforts depends critically on the notion of information hiding, which makes object and algorithm invisible whenever possible to the portion of system that do not need them. So basically, you just try to hide your information from someone that is not relevant to your program. So encapsulating data and subroutine, you need to have information hiding by subroutine is limited, and usually you want to allow people to access your subroutine. And static variable in subroutine allow programmer to achieve information hiding for a single subroutine. The module construct can help achieve this goal for encapsulating data and subroutine. Usually, you can have subroutine as a way to do information hiding, but it's limited. Usually, it just hide those core, but data is difficult to hide. And the data declared in the subroutine actually is not global, will not exist all the time. And static variable inside the subroutine allow programmer to achieve information hiding because static is staying somewhere you can reuse that. So that static variable is hide. So, but this is not really a good technique if you have class. Module as abstraction, a module allows a collection of objects, subroutines, variable types, and so on to be encapsulated in such a way that objects inside are visible to each other. So inside the module, you can see each variable or functions inside the same module, but objects on the inside are not visible on the outside unless explicitly exported. Same thing, objects on the outside are not visible on the inside unless explicitly imported. So import and export are conventions that vary significantly from one language to another, but in all cases, only the visibility of object is affected. The data's lifetime and binding are not affected. As I mentioned early in our talk, this kind of module packaging only used for the visibility definition. Let's look at that chart again. Right here, visibility, we have different level, but it actually only change the visibility or the right to access the data, but the lifetime and binding are not actually changed. So now we look at first kind of module, we call it namespace. Using namespace, we can have class, global, variable, function under one name, and we can change global scope to subscopes. And namespace is a logical compartment used to avoid naming collision. So actually, the reason access the namespace take power, and that actually includes yourself. The naming conflict or collision always occur, and it may occur when same program is using more than one library with some variable or function having the same name. The name collision occur for global variable, global function, and classes. So default namespace is a global namespace, and it can access global data function by preceding double colon operator. As we mentioned, the double colon X can access the global variable. We can create our own namespace, and anything declared within namespace has scope limited to the namespace. And this one actually is talking about this chart we show. that you have certain namespace and you will see multiple sort of stuff here, and outside cannot see you, but you may be able to see some namespace that you inherited or you actually imported, or you actually being called from there. Module as abstraction, random pseudo number generator for C++. Right here, we are talking about one way of information hiding by using namespace. So we in this namespace mark is the module. We have seed that getting from system time, and then we have A, that's one prime number. We have M, that's another prime number. And then we have two functions. One is set seed. You update the seed. Another, the other one is to actually read integer that generate integer random number random integer, and that based on the A value and the M value and the seed, the existing seed, and then you perform this modular operation to create a new seed, and that is the random number being returned. So this one can be run several times to create a pseudo random sequence for your main function. And this variable only visible to set seed and set int inside this module. If the outside module want to access this namespace, then you need to use the namespace double column and then the function name or the variable name. Then you are able to access the namespace. So you can use random module. This E is not needed, and then semicolon, two double column, double column, and then your function name. And by doing this, you can actually run this random number generator. And alternatively, you can import the whole module in using namespace read module instead of just using a certain function. And by doing this, you can run the set seed, and you will see seed, and you will also see random integer generator. And these two methods, the first one uses less memory, but you actually have access to more variable, more functions. The second one actually is take more memory, but actually it will be access to more variable or more functions. Now let's look at this import and export. Some language allow the programmer to specify that name exported from module be usable only in restricted way. Variable may be exported for read only. Variable of that type may be declared, passed as arguments, and possibly compared or assigned to one another but not manipulated in other way. So basically, you allow the programmer to import from other module or export to other module. And a module that name must be explicitly imported into it is called closed scopes. So that's for language like modular or Haskell. A module that do not require import are called open scopes. And language like C++, Ada, Java, and C# or Python are considered to be open scope. So we have closed scope language like Modular 3 language, and we have open scope language like C++ and Java that actually do not need require import to get access to the for Java is to the same package. Outside package you still need to use import. And right here, the modular 3 means that you always need to import or export. Okay. Module as manager. Manager is one thing that module can act as. And in fact, manager just like a object. So let's look at this module. We have namespace random number manager and two prime number, and we have one structure of the generator type. So this is just like an object or data field for the object. And then we have the create function. Create function will return a pointer of generator type. So we create first one generator structure and assign the address to G pointer. And G pointers access pointing to seed, and the seed in this G pointer will get the value from time function that actually is the initial seed, and then we return G, the pointer to the structure. So it actually, when you use this random number generator, you actually use the rand manager module and then double column create. Then this one will create one structure for you, and then you return its address back to G1 pointer and later to G2 pointer. So we have two pointer pointing to generator class. The structure. And then we have seed function, set seed function, and the random seed, random integer function. Both of them will actually are just like methods in our classes. And then we actually can call this random number generator if we use this random number manager double column with the function that we can actually call the random number generator G1, and then get the random number from G1 and then return to R1. Same thing for G2 to R2. But if you compare the class in C++ and module that using the namespace in C++, you will see that class in C++ is easier to understand and shorter. And the way to use it is also easier. You just need to use new random number generator and then create a pointer address, a record address, class object address, and assign it to pointer G. And then pointer G can point to this function and run and return the data to R. And there are dynamic scoping. In a language with dynamic scoping, the binding between names and objects depend on the flow of control at runtime, and in particular on the order in which subroutines are called. So basically, dynamic scoping, the binding between the name and object will depend on the runtime, and that is harder to understand because the word current binding for them is the one encountered most recently encountered during execution and not yet been destroyed by returning from its scope. Right here, I'm going to give an example for the difference between static and dynamic scoping. First, let's look at this example on the right side. We have one global declaration for n of integer type and one local declaration of n of integer type. This n of integer type is defined in procedure second, and we have one procedure first. And main program is right here. So right now, consider the program in the figure 3.9. If static scoping is in effect, the program static versus dynamic scoping should print 1. Okay. Now, if this static, this integer has the power for the whole program except this procedure second. So initially, you have n equals 2. If the integer that you read in greater than 0, you execute procedure second, and then you go to here and you declare a local variable n, but you call first, and you come to first, and then you update n equals 2. So this originally n equals 1. Now it is assigned with a number 1. So at the end of the program, you print out 1. And if the number you read in is less than or equal to 0, then you perform the procedure first, and you will also print out 1. Now, if it is dynamic scoping, then if you have read in an integer that is greater than 0, then you run second, and you come to second, you redefine the n integer and you call first. At this time, it is dynamic scoping, so n is updated to 1, but that one actually you are updating this n equals 1 integer. So when you run first, you update this variable, and when procedure return second return, you come to this right integer, you got a value from this n integer that is set to 2 instead of this one right here. But if you actually have the real integer that's less than or equal to 0, then you execute first. You come to first, you set the integer to be 1, that actually do not have this reference environment. So actually you assign n equals 1 and you print it out. Then this n is referring to this global variable n. So you write out integer n, that will be 1. So in static scope, you print out 1. In dynamic scope, you may print out 2 or 1. Runtime error with dynamic scoping. With dynamic scoping, error associated with the reference environment may not be detected until runtime. So right here, we have figure 3.10. For example, the declaration of local variable maximum score in procedure foo accidentally we define a global variable used by function scaled score. So right here, you actually declare it, and then right here, you actually you have a declaration in the local variable, and then this function scaled is called by foo function. So in foo function, you will call this one. But since you have a declaration of this, so right here, if it is dynamic scoping, you may have the wrong number, not reference to this one, but you will reference to this one for dynamic scoping. But intentionally, you want to have the reference to here, and that is what is intended for. So that will create trouble. If local max score had been an integer, no error would have detected, but actually you are referenced to the wrong integer. So unintended local issue will occur in this case. Now let's look at the next lecture, lecture C8, the meaning of name within the scope. Let's have a brief review for name, object binding, and scope. A name is a mnemonic character string representing something else. So you can have some variable name. These are names, but numbers are not. Or string in double quote notation, it is not named. These are called literals. These are not names, not variable names. And plus sign less than equal to these operators may be named if they are not built-in operator, or if they are overloaded, they can be a name. A binding is an association between two entities, name and memory location, or name with object, or name and the function. So binding is the association between two entities. Typically, a binding is between a name and the object it refers to. A reference environment is a complete set of bindings active at a certain point in the program. The scope of a binding is the region of program or time intervals in the program's execution during which the binding is active. So scope of binding is the interval, time interval or region of program that your binding is empowered. And a scope is a maximum region of the program where no binding are destroyed. So basically a scope is something that your variable is empowered. And these different things are the terminology we use in this chapter, and also there are several occasions that you can declare a binding, like including building time, that's the language derived time, global, that is programming time, enclosed, that's loading time, and the local, that is calling time when a certain procedure or function is called. And in terms of the name, object, and reference, we have such a chart to describe it. You may have a memory location, we call it object. So my class, my object, this is an object. The name, this is the object, and the name is my object. Let us consider this is an entity of the memory location. And the name is my object. And you declare my class, my object. My object is the name. The entity is here. And then you can also declare my class star my pointer. Usually I call it star as body. So body of my pointer is my class type. So my pointer is a pointer to my class type. And the SI, I call it ages. So ages of my object is assigned to something. So that is actually, you may assign the ages to the my pointer. So the my pointer can point into this. And this actually, if you have a pointer, my pointer, star sign my pointer will be body of my pointer is this. So this my pointer is a pointer. Body of my pointer is a my class object. And my object's ages is a pointer's value. So these are the relationship between name, object, pointer, and reference. The meaning of name within the scope. Two or more names that refer to the same object at the same time in the program is said to be aliases. So basically you have two names referencing to same object, and both of them will be maybe accessing or updating the object. We call it aliases. A name that can refer to more than one object, one name, more object, we call it overloading. And redefinition of a name is called overriding. One name, you apply different definition, that's overriding. Overloading related to the more general subject of polymorphism, which allow a subroutine or other program fragment to behave in different ways depending on the type of its argument. So we will explain the overloading and overriding in the next slides. First, let's look at the alias. The alias, what are alias good for? Alias are two names for the same object. So basically we call it two different references to an object. So it's a multiple representation or union of variant are better than alias. And alias is pointer-based data structure, linked list data structure, different way of traversal. And in C++, we can use alias for call by reference. Let's look at this call by reference case. We have accumulate program, and it uses an argument sum. So sum being passed to this accumulate function, and double SI declare this X as a reference. So basically, the reference of this sum is passed to the function. So X become a alias for sum. So X is sum is X inside this function. So sum plus equals X mean the same thing as sum plus equals sum. So sum plus equals sum equals sum equivalent to sum equals sum plus sum. So New sum is 2 times the old sum. And right here, x is 2 sum. 2 sum times 2 sum become 4 old sum square, or 2 times sum parenthesis square. So the sum of square will equal to sum new sums square, or the 2 times the old sums square. Alias and core improvement. Right here, we talk about the body and value. First, we declare A is an integer, B is an integer, the pointer P's body is an integer, the pointer Q's body is an integer. So now we assign P's body we assign to A. So actually you copy the content of P's body to A, and then you have copied the 3 to Q's body. So Q's body you copy 3 in, and then you copy P's body to B. So copy the value, sorry. So copy the value of 3's body, copy the P's body, the value to B. So I'm sorry, this has no 3 over there. And then A and body of P, B, body of Q are not alias. These operations just copy value from the body of 2 pointers. Overloading. Some overloading happens in almost all languages. Integer plus and the real number plus, they are overloaded. Real and read and write in Pascal, function return in Pascal, these are all overloaded. Some languages get into overloading in a big way, especially for Ada and C++. They actually allow a lot of overloading for the operator, especially for C++ and C language. Overloading and the overriding function. Overloading function, 2 different things with the same name, but actually you have different parameter and return type in C++. That's called overloading. So when you call a function, you actually can operate like one function, but actually they are operating on 2 different data types. That's called overloading. That's one way to perform overloading. And polymorphic method, that's different. That's actually overriding function. One thing that can work in more than one way. So actually in modular 2, you have function mean, and then put an array of integer over there. And in Smalltalk, you have other things. But let's look at the next page. And the next one is generic function. Generic function actually is a syntactic template that can be instantiated in more than one way at the compile time. So basically, generic function is something that you can accept different data type. And that is determined at the compile time. And sometimes you will just reserve several type variable that actually allow you to access data of different variable, and they might be generic class or generic function, and generic class may be containing data of different type. And this is via the microprocessor of C++ for macro, and you will insert certain code in a certain function or program that process different generic type without referring the data type. And in C++, you have built-in templates. And this and the previous two, the overloaded function and polymorphic method functions, these are all polymorphism. Let's look at the chart again. This polymorphism chart, you have overloading and overriding function or operator. And this is called Eha polymorphism. And the parametric polymorphism is for generics. That's universal polymorphism, and that actually assigned by language definition, not by the programmer. And Eha polymorphism is assigned by programmers. overloading of enumeration constant in Ada. Let's look at this example. We have a type months, which is from January to December, and we have the print base, that's for print statements, radix base. And the radix base can be decimal, binary, octal, and hexadecimal. But unfortunately, we share the two names, octal and the decimal, with the months October and December. So if we declare a variable of month type, then it will be using this enumeration type set. And if we declare a PB of the print base type, then it will be using this enumeration type. And then we can assign December to months, assign October to PB. These are okay, since you are able to differentiate the two by the data type. And if we print out October or print out October, we cannot determine whether it's from the month or from the print base. So in some language like Ada, it will allow you to print like this. You can assign the data type, months, and then quote, and then parentheses, and put your October inside here, and then you will print out October. And in C# or Modular 3, one can say like this. You can assign months, but using the same prefix way I use for the access of the data field in the record to assign it to months. So it's months.December assigned to this, and print space.October assigned to BB. Overloading of built-in operators. C# plus language allow you to overload your operator. So usually we have the A plus B equals C. We assign the value to C, but that's for integer double data type or floating point data type. But if we have a class that is using the complex number, then we can redefine the operator plus to overload it for the complex data type. So after this definition of the plus operator plus function, you can actually have this C equals A plus B for complex data type. And in C++ and the C#, which are object-oriented, A plus B may be short for either operator plus A, B, or A dot operator plus B. And A dot is actually the object A's member function, operator plus B. This is object-oriented way. Sorry. This is object-oriented way. And this is the traditional way. In the later case, A is an instance of class module type that defines the operator plus function. C# has similar syntax. Now let's look at the series of 2 lectures on binding of reference environment. Part 1 for binding. Binding of reference environment. The reference environment of a statement is a collection of all names that are visible in the statement. So names are visible means it has certain binding. And the reference environment of a statement are all the binding, all the set of binding. And now, in order to specify the binding, we have static scope and dynamic scope. Now let's look at the deep binding and shallow binding. And here we have a pseudocode. This pseudocode actually is not real. It's actually a makeup story. But what it's trying to show you is the shallow binding and the deep binding. The print procedure print selected record is a general purpose routine that know how to traverse the records in database. The database we use is people, and with several persons in there. It takes as a parameter of a it takes as parameters a database, a predicate to make print or don't print decision, and a subroutine that knows how to format the data in the record of this database. So basically, we call this print select record with the database people and with the other than threshold function as the predicate, whether you print out certain person or not. Third one, we had a print service routine, print person. That is actually the function we will try to print the people out. So if we had a print selected record, we actually have one line number being defined over here. And then this procedure will check the device whether it's terminal or printer. If it is terminal, we print out 80 characters for the line length. If it is the printer, we print out a line of 132 characters in the line. So basically, these are the old devices, because in the text mode and the text mode terminal and the metric printer, we have either 80 characters a line or 132 characters a line, but these are no longer in use because we no longer use metric printer that much. So each record R in database is being printed out if the predicate check for this person, the age of that person is greater than threshold, and we will print that out. And when we print that out, we use the print routine function. And in print person, as a print routine function, we actually check the line number in order to print it out. So this line number is to adjust the printer hardware, and this is shell binding because it actually binds to the local, the one who actually just in the same level to code it. That's called shadow binding. And we will look at the deep binding dynamic. We will look at the deep binding case, and it is usually the default setting for the language with dynamic scoping. But let's look at this one is shadow binding. Let's look at the deep binding. Deep binding actually using the same example, but actually I believe this won't happen for most of the language because deep binding is and shadow binding can only happen on certain language, just using one way, not both. But they do have some language that have both features. Now let's look at the deep binding. The deep binding, we have the threshold defined at the top level of the program, and actually right here we have the threshold print other than threshold function for the predicate. And then actually it has the person's age greater than threshold. This threshold actually is tied to this threshold at the top level. So we call this as a deep binding. It's different from the line length. In this threshold case, that's deep binding. Subroutine closure. If your language lets you store subroutine as value and the next subroutine or recursive, then you can make closure. Closure is very simple to understand. It actually is the reference for your subroutine. So a closure is a subroutine that refers to variables defined in an enclosing scope. The closing scope or enclosing scope or the open scope, we will discuss it later. Deep binding is implemented by creating an explicit representation of a reference environment and binding it together with a reference to the subroutine. So deep binding is actually combining the reference environment with the reference to your subroutine. So we'll show one example later. Right here, we have an example for Python, and that's using deep binding. So you will see that when the function call happen, the whole environment being attached to it. Now let's look at it. It actually is using static scoping, but actually all the scoping is decided at compile time. But somehow the binding is deep binding and it's static scoping. So let's look at here how it deeply bind the variables. Now we have the call function with parameter 1 and c. C is a function closure. So we actually pass 1 and c to this function body. And then actually this body of A will check I now is 1, so greater than 1, that's false. Then it will call A2 and B. So 2 and B will pass to here. But remember this B is the B when I equals 1, that we call it deep binding. So 2 and B is passed to here. Then when we run B, print out I, at that time I is actually not this current 2, but the I over here. This is called the deep binding for Python. So conceptually, let's look at this. When we call A1C, we push the I and P into the stack. And then we come down this, and then we call to A to B, and A to B being pushed. But however, this B is reference to the B in this environment of A1B. So that B actually will print out I is actually 1 instead of 2. That's in the environment for this second frame, second call frame. So this show you deep binding that will print out 2 instead of the shallow binding. In the shallow binding case, it will call 2B, and then 2B will be passed to here, and then P will be the B function, and B function will use the number 2, that is shallow binding, and print out 2 for shallow binding. And we do an experiment, and it do show up that the result for the deep binding, we actually print out I equals 1, and that is the variable setting for this I equals 1 here. Lecture C10, Binding of Referencing Environment Part 2, Closure and Lambda. First, I would like to talk about first class value and unlimited event. First class value or first class function is very important concept. A value in a programming language is said to have a first class status if it can be passed as a parameter returned from a subroutine or assigned into a variable. So basically, any value is called as first class value if it can be used as a parameter, as a return value, or be assigned to a variable. So anything it can be done, then we call it a first class value. Compared to first class value, let's look at the third class value. Third class value cannot even be passed as a parameter, so it can only be used as a label. That we call it third class value. And third label is used only for jump from one location to the other location. And in fact, nowadays there are very few of such labels in the modern languages. And something in between, we have the second class value. And second class value can be passed as parameter, but will not be able to return and or be assigned to a variable. So actually, this actually means that the second class value can be used for the right hand side that you pass to somebody else, and then it cannot be used to receive other people's value. So that cannot be used for the left hand side as the left hand side variable. And in fact, most of the common language Most of the modern language only support first-class value now, and second-class value can be seen in Ogo family languages. Now let's look at the first-class subroutine in Scheme. In Scheme, first-class subroutine is in a language with nested scope. Introduce an additional level of complexity. They raise the possibility that a reference to a subroutine may outlive the execution of the scope in which the routine was declared. Consider the example in Scheme on the right. So basically, you may have the binding or the reference actually that outlive the routine outlive the scope that the routine was declared. So let's look at this case. We define f equals to this plus x2, and plus x2 is a lambda expression that defined over here, plus x with the lambda expression. So plus x is replaced by the lambda expression, and we pass the parameter 2 in, so that f becomes this lambda 2 lambda y plus 2y, and that's f function. And f function is replaced by this, is defined by this plus x function, that is a lambda function. And then if we bind in f with the parameter 3, then this 3 is passed into there, and it becomes y lambda y plus 2 and y, because f is binding with the x of 2. So f with 3 will bind to lambda 3 plus 2y. This y actually replaced by 3, but I put a y here to let you know this y should be replaced by 3. And by doing that, actually this last statement will return the value of f and 3, and that is plus 2, 3. That will return 5. And from memory point of view, we have main program actually that define a plus x with the parameter y for the lambda expression, and the value returned will be an enum, and enum is an anonymous lambda expression. So that actually you further define by this f3, and that y passed by 3, so that enum evaluate to actually lambda 3 plus 2, 3, that will read this enum's value is 5, so eventually you will return 5 as the value for this whole thing. So here the last construct in line 4 declare a new function f, which is the result of calling plus x with argument 2. Function plus x is defined in line 1. It returns a unnamed function or lambda expression declared at line 2, but that function refers to a parameter x or plus x. When f is called at line 5, the referencing environment will include x in plus x, so that x in plus x still be used in here because they are sharing the same environment, despite of the plus x had already been returned, and so somehow we must ensure x remain variable. And actually this is some sort of side effect, but that is how Scheme works. And object closure, let me show you a object closure in Java case. In Java language, you have interface, and the interface may have some function. In this case, in func, we have call, and then with parameter I pass in. And this interface is implemented by plus x class. So plus x class will implement the in func. So this call function has the implementation right here. And when we create a plus x object with a parameter 2 that pass to the constructor of plus x class, and that's the n assigned to the variable x, and that actually will get the value of 2, so x become 2, and then this x is 2, so that you actually when you call the function, you will pass 3 in, and then that would be plus 5. And by doing this, actually the f can be assigned by any reference reference address of any plus x address, object's address. And by doing that, f that call the member method of the f pointer will be calling the dynamic bound polymorphic method in the plus x object. And so right here, if you have the new plus x3, that call function will be returning I plus 3, and that return value will be 6 instead of 5. But right here, we actually use the plus x with the parameter 2, and that x is replaced by 2. So when we call f.call 3, that will print 5. And similar closure can be found in C++, but it is not a interface. It will be a object in C++ class case because there is no such thing as interface. But you can see right here, the infun class, it has only one virtual function, and that virtual function has an assignment of 0. This doesn't mean the return value will be 0, but it really means this virtual function is an abstract function, so there is no implementation. And then we have a plus x class as well, and this plus x inherit the public int function, and that is the class. And in this class, it has a abstract function, so the implementation need to be overridden by this concrete class. So the concrete class actually need to implement it. And similarly, you have the constructor for this plus x function, and you pass 2 in. So right here, this n is assigned to x because x is initialized right here. X is in the initialization list. So x is initialized with 2. So x had a value 2. So, and it is a constant. So right here, you always have the 2. And when you use this class f initialized with 3 pass to and actually it should be calling the operator for this. It should call in the function right here, and this one actually is a function that replaces the operator. It is not a constructor to actually create a constructor. So this one actually replaced by the operator, and it will return 5, will print out 5. So object f can be passed to any function that is expecting the parameter of class infun. And that's the way C++ finish the closure. In C#, we have dedicate, and we have 2 ways to use the dedicate. Now let's look at dedicate first. So right here we have a dedicate function declaration, and it's actually is a infun that will return integer type and with 1 integer input. And this dedicate function can be accepting a function that actually we have the creator. If you put a function inside here, and this function actually return I plus 2, and this function plus 2 function will have a dedicate type f, and this dedicate type f, when you put in a 3, this 3 will pass into the dedicated function to accept that 3 and not assigned to I, and I plus 3 that will return 5 and print out. So this plus 2x is a dedicated function, and f is a dedicate. It represents the plus 2. So f, whenever you pass a 3 in, and then you will get the value of 5. And if you pass a 4 here, you will get a value of 6. And this dedicate can also be replaced by a class or object. and this actually has the function call. So right here, instead of using this +2 function, we create a new object. This new object is plus x type with the parameter 2 for the constructor, and the constructor 2 assigned to the x value, and x value passed to the call function. So right here, we actually put in a dedicated function. That dedicated function is the new object's call function, and that's dedicated function. So this call function is a dedicated function, and the dedicate is this G that actually also needs this dedicate infun type declaration for the dedicate. And if we call this dedicate function, put in number 3, that number 3 will be passed to the dedicated function, that is the call function, and actually it will also return 5. And dedicate and unlimited extend. Remarkably, though C# does not permit subroutine to nest in general case, version 2 of the language allows dedicates to be instantiated inline from anonymous method. This allows us to mimic the call of example for scheme. So actually, instead of using this, we can actually put a dedicate right here for this declaration of the plus y function to replace this, and the plus y function actually put the dedicate right here, and this mimic the function for this plus x, and that's that dedicate y actually is a lambda expression using the dedicate to replace the lambda function, and then we actually had this dedicate function that return a dedicate, and this infun is the dedicate right here. So when we actually call this plus y2 function, and actually it returns the dedicate, and the dedicate is the h, and h can be used in the same situation like G, and that dedicate function actually return another dedicate right here, and the 2 will be passed to here and return the value of, I'm sorry, this 2 will pass to y, and y will be put here. So h will assign another parameter for this I, and that is the dedicate of h that is holding another dedicate. Lambda expression, we can further improve that dedicate function by using a lambda expression. So this one actually is used to replace this dedicate function. And lambda expression in C#, you will have one parameter or multiple parameter with parentheses, and then you have the double arrow sign with plus I plus y, and this I plus y will be the return value. So that will be able to replace that dedicate function. And lambda expression for scheme is like this, for C# will be like this, for OCaml will be like this, for Ruby will be like this. And you can check the lambda syntax. I will not go into detail right here. But anyway, all of these 4 lambda expressions had a common function that will be compared the bigger one for, we'll find the bigger one for between the I and J, and we'll return that. So basically, if we pass 5 and 8 into this lambda expression, it will evaluate to 8. And same thing for the other formats. Right here, I'll talk about a lambda expression for C double plus 11. First, it had the lambda introducer and the capture cost. And when you see a equal sign here, that means it's called by value. That means that if this apply to certain parameter list, that parameter will pass to here, and then it's a call by value situation. So value will be passed into here. And then you have the mutable specification, whether it's mutable or not. you have the exception specification, whether you will throw the exception or not, and the return type is integer. And the lambda body, you would have the n equals x plus y, and this y will get the background data, and this x is passing by the parameter. So this x is in the same situation as I you saw before, and that return value will be n. So this one actually is the same as this one, and y would be have some background knowledge, and actually you will pass the I here to sum it up, and I is written as x right here. So in lambda expression in C double plus 11, you have a capture list. Equal sign means call by value. S sign means call by reference. Nothing is a lambda with empty capture clause. So it's the one with no external references. It accesses only the variables that are local to the lambda expression. So you just pass some parameter in. That's it. And if you have J and S sign K, means capture J's value and K's reference. So right here we have one example. There is a for each statement, and for each is a standard library routine that apply to its third parameter. So this lambda expression will apply to the data set specified by the first two parameter. And the first two parameter is the beginning of the vector set with integer. So it will be the first begin integer and the ending integer, and in between this begin and end in the vector will be passed to the lambda expression. So actually this lambda expression will find those vectors elements that is less than 50 and print them out. And right here, this one is for call by value, this one for call by reference. And here is the lambda expression in Java. A lambda expression is like a method. It provides a list of formal parameter and the body. So this is a formal, formal parameter, and this is the body will be the return value. And lambda expression can be put into any location that require a function. And right here we have s as a parameter, and this one will return the length of the string. And this one you have integer x and y that will return the sum of them. This one has no parameter, it will only return the 42. And this one has x and two parameter y and z, and it will return, if x is true, it will return y, and if it's false, it will return z. So this whole lambda expression is equivalent to, you have a conditional statement s and then question mark and then y and then comma and z. It will equivalent to that, and that conditional expression will also be can also be put at any location that this is accepted. Lambda expression in Java, and we have the array sort routine, and this array sort routine actually will put, you can put a array over here and a comparator class over here, and the comparator class is implement this H comparator class implement the comparator interface, and the comparator interface need to override the compare function, and compare function is the core for the sorting algorithm. So now this compare function actually return the integer.compare function. So it used the integer compare function as its own compare function for this H comparator. So right here, you put this comparator function, a comparator object, it actually will return the integer.compare. And this actually is the same with this lambda expression. you have the parameter list, and it will return this integer to compare. And because it is returned at the location that require a function, so this is valid. And this integer.compare function will be used to compare and provide a sorting service for the people array. And integer.compare, and this usage is similar to when you use the event listener for the swing GUI package. Lecture 11, we will be talking about name in compilation process. In the compilation process, we have the source code processed by preprocessor, and then we have compiler compiled to object code, and then we have linker, loader, and runner. And all of these, we are able to provide some sort of binding for name and memory. And actually, that depends on the language and the compiler. And we have done a lot of talking about these different stages. Right here, I would like to focus on the preprocessor part. First, I would like to talk about separate compilation. And C language allow you to compile the code separately. And there is certain module problem between different modules, and you need to use external keyword to allow different module to access the other modules data or functions. And we will show that later. Right here, that we talk about a macro expansion first. We have a program called infback9.c, and actually in this program, it used the macro libit, and this macro libit actually has also used a macro pool bytes, and macro pool byte also use the macro pool, and macro pool is equivalent to this code. And something to remember is that macro is different from function code. So it just expands the code so that you need to check the final code instead of looking at the code right now. And after the expansion, there is no function at all. So there are no cofferent involved in macro expansion. So you need to be careful. It may look like a function, but it is not. So when we define a libit like this, it adds a pool byte in there. So if we put the number 3 and we write down like this in our statement, this libit 3 after the preprocessor will be expanded to this, and this pool byte will be further expanded to this. And then in pool byte you have pool, and pool will be further expanded, and so on and so forth. So the macro is only used for expansion, and in fact, after the preprocessor, the compiler will see the whole program with the expanded format, no more macros. And that is the final code you need to compile for the compiler. So now let's look at the separate compilation. Separate compile file in C provide a sort of poor main module. So it's a very poor design for module, and module only available in C++. The rule for how variable works with separate compilation are messy. Language have been jury-rigged to match the behavior of the linker. Static on function or available outside function mean it is usable only in the current source file as global. Otherwise, it requires a header file and the external code. So in order for other code to use it, you need to provide header file. And if you want to use other people's variable, it needs to be written in their header file, and you also need to specify it by external keyword. This static is different from the notion, is a different notion from the static variable inside a function. Separate compilation. Separate compile file in C is turned on variable or function means that it is declared in another source file. Function header without body are external by default, and external declaration are interpreted as a forward declaration if a later declaration overrides them. Variable of all functions that don't say static or external are either global or common. Conclusion: the moral of the story. Language feature can be surprisingly subtle. Design language to make life easier for the compiler writer can be a good thing. So basically, you need to make the language easier for compiler writer and also make language easier for programmer. Most of the language that are easy to understand are easy to compile, and vice versa. If it is easy to compile, it is easy to understand. Conclusion: a language that is easy to compile often leads to a language that's easier to understand. Good compiler on more machine, more supported, better code, fewer compiler bug, smaller, cheaper, faster compiler, and better diagnosis. So that's why we spend so much time on this name, binding, and scope. The purpose is when you need to design a language, try to make it simple to everybody, but you need to retain some robustness on your language. That's the whole goal. Thank you. Bye.